Alright, in this video, let's finish up our conversation about Chapter 4 in variability. Okay, so we introduced this idea of variability as the kind of quantitative measure of spread, and then we gave an example, when we use the median instead of the mean. If you use the median, you use the IQR, the interquartile range, to kind of estimate the spread or give you a quantitative measure of spread. When you use the mean, you measure spread with what we call the variance. Okay, so the variance, and the variance was the average squared distance, average squared distance from the mean, So each observation, we look at how far away it is from the mean. That was the deviation. Then we square it, and then we add them up and divide by the total population size. But I mentioned in the last video that often we don't have the population size, or we don't have information pulled from the population. And so in this video I want to look at sample variance and sample standard deviation. Okay, so sample variance, which we denote as s squared, lowercase s, and sample standard deviation, which again is just the square root of the variance sample standard deviation, and for our purposes we'll give it lowercase s, which is also used. S, capital D is also used. So this is lowercase, whereas this is uppercase. Alright, great. So let's take a look at some kind of definitions and ideas surrounding variance. Okay, so let's suppose we sampled lowercase n scores from our population. So our sample size is lowercase n. Now if we look at those scores, we have a set of scores, so x would be our list of scores. Okay, when we compute the sample mean, everything's the same, right? So our sample mean looks like this. Big M is equal to the sum of those x's divided by lowercase n. Okay, that's exactly the same as the population mean. We just changed out the lowercase n. In fact, the sum of squares, so when we're calculating the variance, we use sum of squares, and this is kind of the computational method, the book calls it. And so the sum of squares, sum of squares, which we abbreviate SS, and we write it as the sum of the values squared minus the sum of the values squared, and we're going to divide now by the sample total. Alright, so this looks almost identical, right? It looks almost identical, except for this is the only difference right here. We're using little n instead of big N. Alright, so sample mean is almost identical. Again, we're interchanging big N with little n, and sum of squares is almost identical, except for again we're interchanging big N for little n, or flip that, we're putting in the little n. But here's the difference. When you calculate the sample variance, s squared, it's still going to be sum of squares, but now we're going to divide by n minus 1. Okay, and that's a big difference. Okay, that's a bit different. But it's also a big difference. Okay, so in this video I want to explore the reasons why we're dividing by n minus 1 instead of just the sample size, and also explain a bit of reason that's a bit intuitive and some that's definition based. Okay, so the big question is, why is it 1 less than the population total? Alright, so let's take a look at an example. If we had, let's say, 3 scores, our list was 3 scores, and let's say that we knew 2 of them, 2 and 5, and then this unknown value. Okay, if I provided the sample mean, okay, which is, let's say, 7, if the sample mean is 7, you can figure out what that last or that missing score is. Okay, so this is a sample and we know 2 out of 3. So are known. Okay, and we happen to know the mean. So if we think about it, the sample mean again is equal to the sum of the scores divided by n. In our case, this would say 7 is equal to 2 plus 5 plus this unknown value divided by 3. Well, this is a nice simple algebra problem, and we could solve for this unknown value. So we have 21, if I multiply both sides by 3, I have 21 is equal to 2 plus 5 plus the unknown value. This sum is 7, and so we have 21 minus 7 is that unknown. So 14 is that unknown. So we could figure out everything about the sample set by knowing 2 out of 3. So in other words, knowing 1 less than the full amount. So we had n minus 1 known observations. Okay, so that's where the n minus 1 comes from. We call this the degrees of freedom. Okay, that's a funny idea, funny phrasing, but it tells you how many values you need to explicitly calculate the standard deviation or the mean or anything else with that data set. So we need, if I have a sample of 25 observations, I need to know explicitly 24 out of those 25 and the mean, and I can calculate everything else. Okay, so I just need to have n minus 1 of that information. So another way to think of this is this idea of parameters being the thing that we estimate with our sample statistics. And so if we have, so here's our population parameter, okay, and it's, you know, if it's mean, it's mu, if it's variance, it's sigma squared, if it's standard deviation, it's sigma, and we estimate these with our sample statistics. Okay, this is getting into the inferential statistics part. So our sample statistics, we estimate mu with m, which I know mine look the same, but they're not. We estimate variance with s squared, and we estimate standard deviation with little s. If we do not divide by n minus 1, we have what we call a biased estimate. Okay, so we are looking for always for an unbiased estimate, and unbiased means if a statistic is unbiased, it means that the average of all sample variances is equal to population variance. Okay, in other words, you know, so if I have a big population, here's my population in a box form, and I sample from it. Here's a sample, here's another sample, here's a sample, here's a sample, here's a sample, another sample, on and so forth. And I look at every possible sample I can make, and each one of those little blobs is going to have some standard deviation, some variance that's associated with it. And I'm just counting them up. So sample 1, this is the standard the variance for it, sample 2, on and so forth. And if I look at the average of all of those variances, they will equal the population variance only if we divide by n minus 1. Okay, so we use n minus 1 so that we will have an unbiased estimate. Alright, so that's the other reason. So first, because that's what we define as degrees of freedom, we need at minimum n minus 1 observations to calculate the rest of the data set. But also, if we use any more than that, so I provided the minimum, but now I'm providing the maximum. If we use any more than n minus 1, we generate a biased statistic. Okay, so biased meaning it will always give you a result that is either too great, consistently too big, or consistently too small. Okay. So with that, we can look at the standard deviation. So SD, right? Little s is equal to the square root of the sum of squares divided by n minus 1. And again, the sum of squares is equal to Okay, let's take a look at an example. I'm pulling this off of, in the end of the chapter exercises, page 116. I'm looking at number 10. Okay, so at number 10 we have a data set sample of 7 scores. So our n is 7. Our list of scores here we have 8, 6, 5, 2, 3. Whoops, I missed one. 2, 6, 3, 5. 2, 6, 3, and 5. So if we look at part A, it says, do a quick sketch for a histogram. So a histogram, we have here, let's do this. We have values from 2 to 8, so 1, 2, 3, 4, 5, 6, 7, 8. 6, 4, 2, and at most 2 of them, so 1, 2. Alright, so let me sketch this in red. Here we have 1, 2, 1, 2. We have, let's see, so that's that one. We have 1, 3. Let's kind of carry that over. We have 2 5s. So 5, we're up here at 2. Okay, and we have 2 6s. Let's carry that over. And we have 1 8. There we go. Okay, so looking at this is not symmetric, but that's okay. It's maybe pretty close. Let's see here. We're asked in part B to estimate our sample mean and the standard deviation. So I'm going to do this in yellow. I'm going to say, I don't know, kind of when you estimate the mean, you're looking to see, okay, what's kind of a center and based on the values. So there's a lot of values here, high values. I'm going to say it's pulled this way, even though like center wise maybe it's like 4. I'm going to go with like 5 or maybe a little bit more than 5. I'll put in just 5. So I'm going to estimate the mean at 5. And in terms of standard deviation, so how far away are each observation on average? Well, the high is 8, and that's 3 units away. The low is 2, and that's 3 units away. So I'm going to say that the standard deviation is like, I don't know, maybe 1.5. Maybe I'd even go as high as 1.75. So like halfway, the square root of 3 is like 1.78 or something. Okay, so that's how I'd estimate. Let's see, part C, it says compute the sum of squares, the variance, and the standard deviation, and then we want to know how well we did. So to compute the sum, whoops, that's part C. To compute the sum of squares, remember that we're going to take the values squared minus the sum of them squared divided by the sample size. So let's see, the sum of the squares, we have 64. The sum of them squared is 64 plus 36 plus 25 plus 4 plus 36 plus 9 plus 25. And if you add those up, you get, let's see, 100, 125, 150, 186, 190, 199. Okay, now the sum of them, let's see, we should have calculated the mean here. The mean is the sum of them divided by n, and so that's, let's see, 10, 22, 24, 27, 35 out of 5, so that's 7. Okay, nope. Out of 7, and that's 5. Hey, we're right on for the mean, that's good. But the sum of them squared, okay, so the sum of the scores is 35, and if we look at the sum of them squared, that's 35 squared. Let's see, I did this already. It's 35 squared is 1,225. So for us, the sum of the squares is going to be 199 minus 1,225 out of 7. So that's 199 minus 52, so 7, 49, 30, 175, and the difference there should be 24. 24. All right. Great. So the variance, let's switch over to blue. The variance is going to be the sum of the squares, 24, divided by 1 less than the sample size. So that's actually going to be divided by 6, so 4. All right. Our standard deviation is going to be the square root of this variance, so it's going to be the square root of 4, 2. Oh man, I was a little under, but that's okay. So that means on average each observation is 2 units away from the mean. Okay? Let's see another example. Let's take a look at what's another good one? How about number 18? So now we're on page 117. Let's look at number 18. Okay, so it says calculate the sum of squares, variance, standard deviation for the following sample. We have n equals 4 scores. So n equaling 4, and our set of scores 7, 4, 2, 1. And it says, note that the computational formula works well. Note that the computational formula works well. Why would it say that? Well, think about this. If our sample mean is something that's not nice, in this case, it's going to be 14 divided by 4, which is what? That's like 3.25. And then you think, okay, to build up with the definitional formula, we have S is equal to the sum of each one of these minus the mean squared. So that's going to be 7 minus 3.25 squared plus 4 minus 3.25, on and so forth. And what sucks about this is that 0.25, we have to now have 0.75 squared, and we're carrying decimals squared, and it just compounds the issue. So the definitional formula is just not fun. Okay? So what's nice about the computational method is that you don't have to compute the mean. You don't need to know this. I mean, it's not hard to compute 3.25, but you don't have to use it for the sum of squares, right? So what we're going to do is we're going to look at the sum of the x's, which we know is 14. Therefore, the sum of them squared, 14 squared, let's see, that would be, I think it's 256, but 4 and 16, carry the 1, 5, 1 and 4, oh no, what about 196? There we go. So 196, we need to know the x's, the sum of the x's squared, like this. So that's 49 plus 16 plus 4 plus 1. This, oh, that's slick. 1 and 49 is 50. That's 20, so we have 70. Alright, let's think about this. We have 4 scores. Okay, so the sum of squares is going to be equal to the sum of the x's squared minus the sum of the x's quantity squared over the sample size. So this is going to be 70 minus 196 over 4. So that's 70 minus 4 into that. Let's see here. 4 into 16 is 4. So that's now 36, which is 9. And 70 minus 49 is this one right here. So that's 21. Okay. Now, to calculate the variance, so s squared, we look at the sum of the squares divided by n minus 1. So that's 21 divided by 4 minus 1, so that's 7. And then the so that's variance. And then our standard deviation would be the square root of 7, which off the top of my head I don't know what that is. It's 2 point something. Yeah. 2 point something. Alright, there we go. If you have any questions, feel free to send me an email or give me a call. And if you're getting stuck on the homework, let me know as well. There's a few items that we cover, let's say in number 15 or 16, where we actually transform the data. And just a real quick overview of number 15. If we had scores 82, 88, 82, and 86, we don't have to carry the 80s, right? We can look at a transform score by subtracting everything by 80 and look at 2, 8, 2, and 6. Compute the mean for these and then add 80 back to it. Okay, that's just for the mean. So the mean of these, 2 plus 8 plus 2 plus 6 over 4, 10, 18, 18 over 4. So we're just finding the average of the additional pieces. Okay, so 18 over 4, whatever that is, 4.5. And so really the mean of these is 84.5. Okay, the average. Okay, when it comes to standard deviation, when you look at the sum of the squares, what's nice about this, if you transform the data, nothing happens to the standard deviation, or I should say nothing happens to the variance. So the mean is transformed by the same amount, but nothing will happen to the standard deviation. So you don't have to compute the standard deviation of these. You can compute it of the transformed data and it'll be the same. In other words, we're really only looking at the difference. Since we're all in the 80s, we're really just looking at the difference between the ones place. So that's kind of helpful on 15 and 16. You can manipulate the data, but it doesn't change the standard deviation as long as you do the manipulation to every data point. Okay.